Now, I want us to look at the derivative as a function. Let's write down. We find out that we can find the derivative by taking the limit as h approaches 0 of f at x plus h minus f at x all over h. Now, this is where we're still at. We can do a lot about this function. We can graph it, we can find subsequent derivatives like the second derivative, the third one, or fourth order, as long as we have a function that it is differentiable to that order. Now, it's important to realize that this is a function by itself. Now, in our previous video, we found out that the derivative of f at x was 2x. And this is clearly, we can graph it. And our x value, if we put them in f, in the derivative function of f, they can give us certain output. Now, you can find that at 1, our output will be 2. So it is definitely a function. Most of them will be a function. Remember that there are rules. It will not be a function if it gives out 2 elements in a set. Now, let's look at whether we can visualize the function of the derivative by using the original function. Let's say we have a function, we have a curve. Let's draw this curve as, let's say it goes nicely like this, like this, like this. That was 2 vertical, like this. Let's extend it a bit here. Oh God, I hope I'm still in the frame. Now, this is our function f at x. Now, by just using this curve, we want to see if we can visualize how the function of the derivative will look like. Now, this is very important. If we look at some interesting points, this way it changes. This will be my first interesting point. Let's take one there. Let's take one there. Let's take one there. Let's draw it nicely so that it's easy. It's easy to explain. Now, remember that this is just a curve that I just came up with now. So it won't always be at 0 like this, whatever function that you are working with. But I see that it might make it harder for me to explain that I put them on 0. Okay, now let's look where our function is increasing. If we draw gradients along the function as it increases, we will notice that all our tangent lines have a positive gradient. Even if you come to this side, you will see that if you draw tangent lines where our function is increasing, the gradients of the tangent line are all positive. So we can conclude that when f at x is increasing, the derivative function will have positive values. because remember that the derivative function is the slope at each point where the tangent touches. So if these gradients of the tangent are all positive everywhere where the function increases, our function of the derivative will have positive values. And by positive values, I mean that it will be above the x-axis. So we will find our function above the x-axis, only where our original function is increasing. Now, let's look at what would look like. Now, the gradient at 0 here, it is clearly, remember that when a line is horizontal, the gradient is 0. When it's vertical, we are not even interested in it. Now, this is clearly a certain value. It's not 0 and it exists. So it's not here at 0, it will be somewhere up there. Let's give it some high value here. Now, the gradient here, we are now drawing the function of the derivative. It will start up here because the gradient here is high, and this, what I'm plotting now, is all the points, the gradients at the different points of the original function. Now, what you have to realize is that these tangent lines, as they go until they reach this peak point here, the gradient here is 0, and here it's some high value here, which means that as they move like this, the gradient reduces. And we say that if you move on a curve and the gradient keeps on moving, that function at those points is concave down. Now, as the gradients reduce from whatever value it is here, they keep becoming less steep and less steep until they reach 0. So, which means that the function of the derivative is decreasing, because the function of the derivative gives us the gradient. So if the gradients are decreasing, that means the function of the derivative is decreasing also. It will start at some high value and then go down, go down, go down, go down, go down until it reaches 0. Now, this is where y is equal to 0. Our derivative function here will be equal to 0. As we can see that here at this point, the gradient is horizontal, and the horizontal gradient is equal to 0. So it makes sense that at this point, our gradient will cross the x-axis, will be 0, as you can see there. Now, I want them to look different, so let me use a white chalk here. Now, here's now another interesting thing. If you draw the gradient now as our function decreases, you'll see that these gradients are now negative. Remember that a gradient that is going down is negative, and a gradient that is going up, it is positive. So this gradient on this side, you can see that they all have negative values. So that would mean that our derivative function, which represents the gradient of a function at certain points, will now be negative, because these values of these gradients of the tangents, if they are negative, then the function of the derivative also will be negative. So it will be below the x-axis. So it will be on the negative side. So it will play around under here. So it will go down, go down, go down, go down, go down, until it reaches this another interesting point. Now, this gradient, they started from 0 and started to increase, become larger but we know that they are negative. I know this is counterintuitive. You'll say, no, -5 is less than -2. I understand that and I agree with you. I'm just saying, if we look at the gradient itself, the value 5, it is greater than the value 2. So this gradient becomes steeper and steeper and steeper. But once it passes this point, it starts to become less steep again. It starts to become less steep again until it reaches 0 here. So this point where the gradient changes from either becoming more steep to becoming less steep, or changes from being less steep to being more steep, then I think I should be saying steeper. So we call that a point of inflection. Point of inflection. Now, the interesting thing about this point of inflection, remember that this gradient went from positive, 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 0, negative, negative, negative. So our gradient has been decreasing until it reaches this point, and now it's starting to increase. But if it was +5 here, it now becomes +4, +3, until it reaches 0 again. So now the function becomes concave up, and a point where a function changes its concavity, we call it a point of inflection, which means that point of inflection, our function will change its direction also. Instead of going down, it will then become horizontal here, and then the function here is increasing. So the gradients here start to increase, so the function of the derivative will also start to increase, start to go up, because the gradients here are no longer becoming more steep, they are becoming less steep. So this function increases also until it reaches 0 and passes the x-axis. So it should be making sense now. But I just want to go just so we both understand it, we get a real touch of it. But I'm gonna go faster now. So from this point on, it's increasing. So it will be, remember, when a function is increasing, the function of the derivative is positive, because the tangents here are now going up. So a gradient that is steep like this will be positive. So the function of the gradient, the function of the derivative, will be above the x-axis. So it will, these values go from 0, increase, increase. So our function will increase, 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 until it reaches another point of inflection here, where they were increasing, 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 and now they are turning. So they are now decreasing again until they reach 0 there. So our function also will start to decrease from that point on until it passes 0, where this gradient here is 0. It will keep going like that. It's decreasing here, so it will be below, 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 below. But our point of inflection here is where our function will change direction also, as this function now becomes concave up. Here it was concave down, so it will pass the x-axis again, where the gradient of the original function is 0. Now here our gradients again are positive, so the function of the derivative will be above the x-axis, going. Now I forgot to note here that if f at x is decreasing, then the function of the derivative will be less than 0. It will be below the x-axis. Now, if this curve is so smooth like this, it doesn't bend a lot. It becomes I think I made it more straight than I wanted to be, but if it's so smooth that it looks like it's not changing gradient, if the gradient here you find out that it's 3 and it goes up staying as 3, then it makes sense that a function of the derivative also will then become constant, because at any point here the gradient is 3, 3, 3, 3. So even here our point will stay at 3. The function of the gradient of the derivative will also stay at 3. So that's how you visualize the function of the derivative. Things are getting interesting now. Now let's say we have our function f at x squared. The derivative function will be 2x. Now if I quickly draw the function of x squared, and then draw the function of 2x, it should be something like this. Now it is interesting to see that here where the gradient of the original function is 0, the gradient is horizontal, also 2x passes the point 0, and as the gradient of the function 2x, the function itself is decreasing, then our 2x also is below the x-axis, and as it is increasing, it is above the x-axis. So the gradient will be 0, it will become 1, 2, and then it increases just like that, just like that. And if your curve is smooth enough, then the gradient will probably give you a nice straight line like this, just like we see that the function of the derivative is a straight line. So see you in the following video.